We are delighted to have Chia-Hsien. I hope that's how you pronounce your name, right? Chia-Hsien? Yeah.
Yeah.
Um, um, we overlapped during our time in San Diego. I say we overlapped. We were in San Diego as postdocs at the height of COVID, so we didn't see each other much. I only got to see him after COVID when I went back to San Diego, and he was already in the process of moving out of San Diego at that point. So Chia-Hsien did his PhD in Caltech with Cliff Chung, and he has worked on a variety of things, starting from scattering amplitudes, double copy formalism, how to look at gravitational amplitudes, especially with respect to black hole dynamics. And in San Diego, I believe you worked with Anish on EFTs. And now you of course have a junior position in Taiwan. So yeah, I mean, we are delighted to hear from you. So yeah, take it over.
Okay. Yeah. Thank you very much, Stephen, for a very nice introduction. So the share screen, is that okay? You guys can see the slides. Yeah. Okay. Cool. Yeah. So yeah. Sorry. Also, sorry for changing the title in the last minute. So I decided to talk about something ongoing and some more unpublished works. So this is based on two parts. On the first part would be the paper from last year with a bunch of amazing collaborators. Benoit Assi with the postdoc at Fermilab, Andreas Helse, who's a postdoc at Cern, Anish Manohar, my supervisor at San Diego, and Julie Pages, whom I believe will visit Australia soon in December. And the second part, I'll talk about some ongoing work with my student Yo Peng. And so this talk will be understanding the structures in RG from fundamental principles. But first, let me ask the question that how do we find the future in beyond standard model physics? So there are two possible scenarios in this search for new physics. Say in the Large Hadron Collider, this is the cross-section in terms of energy. There's one scenario like the search for Higgs that we have enough energy to probe the new particle. So in this case, we have enough energy, so the search strategy will be focusing on direct searches, aiming for these bumps in the cross-section. But there's a second scenario, and which looks more likely the case for the LGC, that we might just have not enough energy to probe the new particle. In that case, the solid line is an experimental observation, and the dashed line is some standard model prediction. So in this case, the strategy should be focusing on precision measurement, and the LGC data may be some precision measurement data for the standard model for us to give us guidance for future search of new physics. And so for this precision measurement scenario, if that's the case, it's intuitive to say let's parameterize our standard model with some unknown coefficients. So for instance, this is so-called kappa formalism, like these vector boson scattering, the 3 vector bosons, so 4 vector bosons. You just multiply some coefficients in front of the standard model process, and which people call like kappa 3 or kappa 4. The problem with this naive parameterization is that these processes, they're related by gauge invariance. So you can't just multiply the coefficient for one process without multiplying the other. And this, or put in other words, this parameterization is not a gauge invariant one. And so for this search for new physics, we imagine we have some new particles that's beyond the reach of our energy scale. But we can integrate out this new particle and formulate the physics in terms of the EFT framework. So this is so-called the standard model EFT, where we have the standard model and we add the higher dimensional operators for integrating out this heavy particle at the scale lambda. And we organize the effect of this in terms of 1 over lambda, so starting from dimension 5, 6, 7, and so on and so forth. And the advantage for this framework is that this formalism is model independent because we express everything in terms of these higher dimensional operators in the EFT. And so for this self-consistent. For instance, we only write down operators that are gauge invariant like the field strength, etc. The downside for this framework, as you can see from this counting of the number of interactions or the number of Wilson coefficients, is that the degrees of freedom grows very quickly when we move on from one order to another. So for instance, at the dimension 6 level, we have about order 100 Wilson coefficients before, this is even before we include the flavor structures. And once you move on to 1 over lambda to the 4th or dimension 8, we have about order 1,000 operators. So clearly that we need to find some hidden structure among this large number of degrees of freedom in order to guide us where the future is for new physics. And in this talk, I'm going to focus on using fundamental principles. The two principles I'm going to use, the first one is field basis invariance, and the second principle will be using unitarity. Okay. So even though for this talk, I'm primarily focusing on the standard model EFT, but the power of effective field theory is that this is a really general framework. So you can start asking things about quantum gravity, which is like effective field theory for string theory, or inflation, heavy quark, all the way down to condensed matter. Or another large area I've been working a lot is the classical gravitational waves. And so some of the structures I talk about today may have the chance to generalize to these systems because they're coming from very fundamental principles. They are universal. Okay. Oh yeah, by the way, so feel free to interrupt me if you have any questions. I hope this is more interactive. So for the first principle, I'm gonna focusing on field basis invariance, which is a statement that all the physical observables, like scattering amplitudes, they're invariant under field redefinitions. So when I say phi to delta phi, the result is the same as the scattering amplitude calculating from this local field phi. Or put in other words, the local field description is artificial. The more invariant one are the physical observables. So before I jump to the field definition, let me give a very simple reason why this can be powerful. So let's take a step back to the well-known QCD. So back to when we learned how to calculate the 1D beta function in QCD, you can ask, what's the simplest way to obtain the beta function? So in principle, you have to calculate all these possible diagrams. These are the normalization factors for the 2-point function, 3-point function, 4-point functions, etc. However, from gauge invariance, you know that the process with 2 gauge bosons and all these higher orders, they're circularly related by gauge invariance. So the key is that if you can manifest the underlying gauge invariance, which this is what we use where we use the background field gauge, the first diagram is sufficient to cover all the results from this second and third diagrams. So putting in other words, using gauge invariance, it can reduce the computational cost from calculating this normalization. So we want to play the same game for the EFT using field basis invariance. And there's actually a second motivation, which is that for the EFT I mentioned, there's a large degrees of freedom. And instead of calculating one operator at a time, we hope to have a more general framework where we can incorporate at least some towers of these EFT operators. So these are two motivations for using this field basis invariance. So one thing I want to emphasize is that the number of interactions I showed before, like order 100 for dimension 6. So field basis invariance on these numbers, like what is already after using this field basis invariance. So we're not gonna shrink down the degrees of freedom because these are already physical, but we're gonna see some hidden structures where different Wilson coefficients can show up hand in hand while doing one calculation at a time. Okay, so let me first give a brief review on this so-called geometry for scalar EFTs. So let me start with something very simple. So just take a bunch of scalars with the favorite index I and j, and then we have a simple Lagrangian with only 2 derivatives. So for this simple Lagrangian, you can consider this usual kinetic term is promoted to some function of phi, which I call hij, and some potential v. And for this h, once you expand in terms of your field, the first order is the usual kinetic term, delta ij. And the second order and the higher orders, these are expansion in terms of field, and you have different coefficients, like a Taylor expansion for this function hij. And you can ask, okay, this function incorporate an infinite tower of operators, but are all these coefficients independent? Okay, so that's the question. And to answer this question, we want to use field definition to eliminate all the redundant degrees of freedom. But there's a very intuitive way how you think about the field definition. The statement is that if you consider the field definition for phi go to phi prime, that doesn't involve the derivatives, the partial phi. This map, if you think about this as like the pion, which has some the vacuum manifold describing by the Gaussian bosons, this field definition is like a change coordinate on this vacuum manifold, which has one-to-one correspondence to the diffeomorphism we do in GR when x goes to x prime. And we have a lot of well-developed technologies in GR. So for instance, we know how to write down covariant derivatives instead of partial derivatives that manifest the transformation property. And likewise, the curvatures also transform properly under this change of coordinate. So you can use this technology and one-to-one map to the quantities. They are invariant under this field basis, change of field basis. So for instance, the onshore amplitudes are invariant. The RG equations are also invariant. And to be more precise, the onshore amplitudes, we have to specify the external legs. So they're covariant, not invariant. But still, you can use all these tools from differential geometry to construct this quantity physical observables that we expect to be invariant or covariant on their field definition. Okay, so once we know that, let's consider back to this very simple example. So for this simple two-derivative Lagrangian, we can perform the field definition. So let me just call my phi prime as a function of phi. And the partial phi will transform in this way, where it behaves like a vector because this prefactor is the same when we do a coordinate transformation for a vector in GR. And once you consider this new Lagrangian, if you write in terms of this second derivative form, you have a new hij which transform in this particular way. And this is a very familiar transformation, just like metric in GR. And therefore, this function hij, you can interpret this as the metric on this flavor space or the manifold of your scalar space. Okay, so once we know this, then you can pull all the technologies you learn in differential geometry. So for instance, now you know how to write down the covariant derivative, Riemann curvatures, etc., etc. And particularly for the scattering amplitudes, say for 2 scattering, it's a function of your external flavors, like IJKL. And when we do field definition, we are only sensitive to linear term, where this is like a global rotation of your scalar. So in other words, on the amplitudes, they're only...
Can I ask a question? Sorry, I cut you off. Presumably, if you expanded hij, so you'll have some linear term plus some first order term plus some second order. So, and all of these would presumably come with some kind of Wilson coefficient sitting in front of it. So when you do a field definition, under RG, you expect those to be renormalized, right? So does it still preserve the curvature structure under renormalization or so-called diffeomorphism?
Great question. Yeah. So for so basically this is like a general version of the nonlinear sigma model, like a two-derivative version. So the normalization, so this coefficient, the Wilson coefficient doesn't renormalize to itself. It renormalizes so it only renormalizes when you interfere with this potential or the renormalizable part of the potential. But you can still ask, okay, are all these coefficients, can remove them by this field definition? So that's the thing we want to explore using this geometry. And of course, they will get renormalized, which which is the main part of the talk, that how we're gonna use this geometry to streamline the minimization calculation.
Okay. Okay.
Great. Okay. Yeah. So thanks for the question. Because of this rotation, so the amplitudes really behave like a covariant quantity. So this U is like this partial phi partial phi is the vector transformation part. So we expect the amplitudes will be some covariant object under this geometry defined by this metric. All right. So let me just take a very simple example. So consider just 4 scalar scattering. So naively, we say, okay, the scattering amplitude is just given by the potential lambda phi 4 term. So first term is coming from this lambda phi 4, which is the 4 derivatives acting on the potential. But remember that the metric, they also depend on phi. So we actually have a second type of diagram, which has a scalar exchange. So this 3-point vertex can be the phi q coupling from the potential. But this we also have a second type of cubic coupling coming from the kinetic term. And this will be in the form of partial h because we're extracting the linear part of the potential. And if you work out details, you'll find that this actually will form the usual crystal symbol in differential geometry. And therefore, when you combine these two types of diagram, which is the physical scattering amplitude, the physical scattering amplitude will combine into this very nice form of the covariant derivative. Because if you remember, the covariant derivative is like the partial plus the additional terms from crystal symbol. So that means that in terms of diagram by diagram, the results are not covariant. You have these partial crystal symbols. But once you consider the physical properties, like scattering amplitudes, the quantities are covariant in terms of this geometry. Or put in other words, using geometry, you know that these two terms have to come hand in hand together because only the combination forms the covariant object. Cool. Okay. Any questions so far? All right, so once you have this notion, then you can do more the full calculation. So for instance, the 4-point amplitude, we have this covariant derivative on the potential, but also for the kinematic part, we also have the Mandelstam Sij, and the prefactor, you can find out that it's written in terms of the Riemann curvature. And likewise, for higher order amplitudes, it's always written in terms of these geometry building blocks. And of course, if you didn't know about geometry when you expand, this can be, the expression will get much longer, but the geometry is a very efficient way to combine different terms together. And you can also apply this geometry viewpoint to other relations among the scattering amplitudes. For instance, the self-servant can be also written in terms of this geometric covariant derivatives. All right. Yes.
Sorry, so do you ever get terms like r square, or is it always derivatives of r or linear? I mean, you don't probably ever, or maybe you can just redefine r squared to look something like r eventually.
Let me see. I think you'll probably get r. Okay, for sure you'll get r squared. So imagine if you stick together 2 4-point scattering to make it into a 6-particle scattering.
Yep.
So of the 6-particle scattering, it has like this factorization, which is written as the product of the 4-particle scattering, which each one of them has an r.
I see.
So when you go to higher order, you'll see like r squared.
Mm-hmm.
Okay. So, all right. Other questions? Okay, if not, let me say why are people interested in this problem? So one of the primary applications of this framework is to answer the question about the nature of electroweak symmetry. So you might think, okay, this something sounds like trivial, but even if you consider the standard model, so if I consider the Higgs droplet, let me write in terms of the O4 scalar. So I can have the usual parameterization where the Higgs is like the radial mode away from this vacuum expectation value. And in this case, the electroweak transformation rotation is like an O4 rotation and the scalar transform linearly. But on the other hand, you may also want to write down the Higgs as exactly the radius of this O4 vector. So in this case, the angle, this n vector is the angle which is constrained to have a unit length. The angles that will transform non-linearly under the O4 rotation. And in this case, this H, you can also collect Higgs. And these two different H, this Roman vector and this text H, they have exactly the same physical amplitudes because they're the same to the linear order. But one looks very nonlinear under electroweak symmetry transformation, the other looks linear. So it just means that when we try to answer whether the symmetry is realized linearly or non-linearly, it can depend on the representation they use. So the question is like, how do we find the representation? If the electroweak symmetry is linearly realized, can we actually find the representation that transforms nicely? And of course, in standard model, the Lagrangian is trivial, so it's very easy to answer that. But once you consider effective field theory, it becomes very non-trivial. So you can choose to write down the higher order operators in terms of the standard model Higgs doublet, which transform manifestly linear under electroweak symmetry. So this is like the circle here, the standard model EFT, which contains the special case of the standard model. But you can also write down the Higgs, the EFT with the Higgs and other boson-boson mode. In that case, this belongs to a larger class of EFT, the so-called Higgs EFT, where the fields can transform linearly. But as I said, the example I gave before, the field, even though it might look like it's linearly realized, but secretly may contain the linear representation, which belong to this pink circle. So this is a very coordinate if you use some Lagrangian, the answer is very unclear because you're obscured by the choice of coordinates. But this is something that geometry can help you because something transformed linearly means that just like the standard model example, around the origin, the Higgs doublet is the linear representation. So question would turn into whether on your scalar manifold, you have a point which is invariant under the O4 transformation or the electroweak transformation. So this is a question you can ask, you can answer concretely using this geometry framework. Okay, but for this talk, the main application will be focusing on calculating RG equations. And the naive, the standard way to calculate the 1D divergence is that we split the field into the classical background plus the quantum fluctuation, and then we integrate out this quantum fluctuation to obtain the effective potential. So for instance, we will have these different types of diagram depending on how many external classical backgrounds that you insert. And different diagrams, again, look totally unrelated. However, if you want to, just like the gauge invariance case, the example I showed before, it's possible that different diagrams may be circularly related if you use the field basis invariance. In order to manifest the field basis invariance, just like the QCD, we want to use background field gauge. So in this case, we also want to choose a good parameterization for the quantum fluctuation that behaves nicely under field definition, or behaves like a vector under this change of coordinate. And so it turned out that you actually don't want this naive linear parameterization, this phi equal to phi bar plus eta, but instead you want to pick something that's more natural from geometry point of view, that you want to parameterize the fluctuation as the geodesic lines away from the classical background, which this parameterization gives you this phi in terms of phi bar plus this higher order in terms of the quantum fluctuation eta.
Sorry, this is only one loop, right? Sorry, I cut you out again.
So
I'm
this
sorry, I should stop doing this.
This nice property, you can derive this to any order because it's just a solution to your geodesic equation. Here, I only show second order in eta because I'm only interested in one loop. But say to two loops, then you'll include like third order, fourth order, etc. And like for instance, like Judy and Anish and others, they have a paper doing this for two loops.
I see. Thank you.
Okay, so once you have this second order variation, now if you consider the fluctuation of the action, you can see that the action actually condensed into very simple form. So for instance, the potential reduced to this covariant derivative on the potential instead of partial. And this term corresponds to the Riemann curvature. And the d mu eta, these d's are not just the usual gauge covariant derivative, but including this critical symbol such that this entire thing transforms nicely covariantly under geometry. Okay, so once you have this simple form, then you can do the one-to divergence, and it again takes this simple result where the y behaves like the field strength, but defines through this geometric covariant derivatives, and the x again is some function that only depend on these geometric building blocks. So in the beginning, I said in principle these are three different types of diagram you have to calculate. But in practice, once you use this field basis or field redefinition invariance, you only have to focus on a few diagrams because the rest are just fixed by this field redefinition invariance. And that's the result from Alonso, Manahar, and Jenkins. And so this is a very interesting framework for doing EFT. And there are, of course, different extensions. For instance, you can consider more general field definitions, the one including derivatives, which on the correspondence to geometry then becomes very non-trivial. You can talk about higher loops, which I just mentioned from this reference, higher spin, including gauge bosons or fermions, which is our contribution to this direction. Okay, so before I move on to fermions, any questions? Okay, great. So now let me talk about how to generalize this geometry framework to the fermionic sectors. So the idea is very simple that just like the scalar case, you want to promote a function into a function of scalars. So now you do a very similar thing to the fermionic sector. So for instance, for the kinematic part, we have the usual psi bar d slash psi, and the Roman indices, these are the flavor indices for the fermions. And we simply promote the prefactor as a function of your scalar field, like the Higgs doublet. And also, for instance, the Yukawa coupling, instead of the usual Yukawa coupling, the mass m is also now an arbitrary function of your scalar field. And likewise, we also have the dipole term, which behaves like a gauge field, the analog of gauge field for the scalar. And for all these interactions, you can find the analog the examples at the dimension 6 levels. So for instance, in the so-called Warsaw basis, this kinematic prefactor, the metric, is chosen to be 1 in the usual basis. And for the Yukawa coupling, this mass matrix M is promoted to have this H dagger H prefactor acting on the usual Yukawa coupling, and likewise for other operators. So this Lagrangian is sufficient for the dimension 6 operators up to the 4 fermion operators, and also covers a large chunk of the dimension 8 interactions as well. And for the field definition, because the fermions, they are Grassmann, so you can't do just a arbitrary function of the fermions. So instead, we consider this type of field definition sending psi into psi multiply this rotation matrix, where you can think about this R is a rotation matrix parameterized by your scalar. And then just like the scalar case before, you can ask how these different components transform under this field definition. So for instance, the metric K will transform in this way, sandwiched by this inverse rotation of your rotation matrix R, and likewise for mass matrix, dipole interaction, and it's slightly non-trivial for this spin connection, which behaves like a gauge boson because it has this non-trivial part to cancel the ultra terms from the kinetic term. So once you have this, yeah.
Sorry. So I have a question. So you are agnostic to the the Dirac or the tensor structure, in the sense that if you had gamma fives or something, okay, so I'm not saying specifically in this context, but if you had gamma fives or something, I mean, do you run into things like evanescent operators or, things like that?
Evanescent operator, great. So you run into that problem when you consider loops. So of course here, you're not gonna encounter that problem. For when you go to one loop, let's see. So we haven't explored the events and operators in this framework yet. Yeah, I would say that you probably still do a similar thing, that you can still promote these functions as scalar phi. The framework doesn't depend on specific dimension,
Right.
at least the geometry part.
I see.
So I would say it's probably okay to deal with events and operators as well, but we don't know.
Okay. All right. Okay. Thanks. Okay.
Can I ask one quick question? So this one here
Yeah.
doesn't contain then 4 fermion operators, right? So they wouldn't be
That's right. Yeah.
included yet.
So there are
Is
two
there a way to include
different
them?
ways you can include the 4 fermion operators. So one is that for this particular structure, so here we assume that this prefactor is just a function of phi. But you can also include this as fermion bilinears. That's one way to include the 4 fermion operators. And likewise, you can also try to do this for other functions as well, like these mass metrics. You can also promote that to a function of fermion bilinears. A different way to add 4 fermion operators is just to say, instead of try to absorb these 4 fermion operators inside this known Lagrangian, you just add a separate term that is like 4 fermion operators with a coefficient, which now you promote into a function of scalars. So there are different paths you can try to pursue. Yeah. And in one way, it's like the 4 fermion operators is like an extension for this function to be depending on the fermions. And the second way would be that you have a new building block in your geometry, which is transformed separately by its own. So kind of up to you what you want to deal with that.
Yeah, thanks.
Okay. So once you have this transformation, now you can just follow from geometry. And because now not only we have fermions, we already also have the scalars I mentioned before. So your fields is actually convenient to think about them as like a super field, quote unquote, because the EFT here we consider are generic, so they don't have the actual space-time supersymmetry. But it's convenient to think about the components as like a superfield. And when we do a coordinate transformation, the space not only has the bosonic direction, the scalar phi, but also has corresponding directions like psi and psi bar. So for instance, for the coordinate transformation, like this one we talk about, the coordinate transformation now will mix fermion and scalar. So you'll have this generic 3x3 matrix for your coordinate transformation. And then you can ask, what's the metric that will transform nicely under this coordinate transformation? And this is how the metric look like. So for the scalar component, you have the same scalar metric as before, but then you also have some non-trivial off-diagonal elements from demanding that the metric transform nicely under this transformation. So there's actually a well-developed mathematical field called supergeometry or supermanifold, where people think about the coordinates are not just boson, but also include Grassmann variables. And the only slight difference from the usual geometry is that you have to take care of the signs -1 from Grassmann variables. But it's very similar to the usual geometry. So for instance, you can write down the Riemann curvature, etc., just like the following the usual recipe. So for instance, if you consider physical scattering like fermion and the scalar, the 4 particle scattering looks like this structure, very similar to the scalar case before, which is linear in the Riemann, but it has this kinematic structure depending on the usual U bar P/U, and likewise for the 5 particle scatterings. So again, geometry really combines things together because remember, this R is some complicated function in terms of these building blocks. But using geometry, you know that they all have the same prefactor fixed by the geometric principle.
So do you have an algebra that connects this? I mean, this is presumed. So this is not n equals to 1. I mean, is this Do you have an algebra
Okay,
that
so
connects the?
there's no the supersymmetry. This is a superfield for non-supersymmetry theory.
I see. Okay.
We just group together the phi, but it doesn't have the usual supersymmetry at all. So, for instance,
see.
we're
Okay.
using language to describe standard model EFT, which doesn't have SUSY. But
No,
we
so
just
my
try to
point
combine
was
it.
right. No, my point was the following. So normally you could. Okay, I shouldn't say normally. I mean, once you've written down a superfield structure in terms of, and this is something we saw as well in a separate context when we were looking at something related to compact theories. You normally get out you can sometimes get out something that looks like an n equals to 2 algebra when you combine some of the algebraic structures in a very specific way that respects diffeomorphism. And that's why I was wondering if there is a way in which you can combine these to get an algebra out or something. But okay, it's not, it may not be possible.
We don't know.
Yeah.
We haven't really explored how this is related to the usual SUSY. So for instance, is there anything special about this geometry if you're actually talking about a supersymmetric theory rather than something generic? So that's something we haven't solved. Yeah. All right. Okay, and so to derive the 1 to RG now in this supergeometry language is also very similar. So you want to define your fluctuation follows from the this geodesic equation. So for instance, this entire multiplet, you have the linear part, but you also have nonlinear part on that mix fermion and scalar together, which is relevant when you consider loop with both fermion and the scalars. So I'm not gonna go to the details, but it's also straightforward to calculate the 1D divergence. So in the first paper, we derived the 1D divergence with fermionic loop, like what I showed here. This second line is fermionic. And the resulting 1D divergence is also very similarly only given by these geometry building blocks, like the covariant derivatives in terms of geometry, and all these D are the covariant derivative depending on these crystal symbols. So without having this geometry, you would have calculated different diagrams, but they all have the same coefficient because of this geometric invariance. And in terms of the actual SMEFT, so for instance, this mass Yukawa matrix, it has the standard model term. You have the dimension 6 contribution, dimension 8, and for the mass dipole, we also have starting with dimension 6, dimension 8, etc. And this dipole operator, because of the structure of the gamma matrices, you always have this chiral combination. So now you just plug in this the actual expression in SMEFT and to this 1D divergence formula and calculate the RG equations. And one advantage for this geometry framework is that you have this compact form for the RG equations. So for instance, here I showed you the dimension 6 operator with d squared h to the 4th. And you have a few simple terms where each term is actually a very non-trivial combination of all the operators that can show up. So put in other words, these are more degenerate from this RG point of view, but using geometry, we know that they have to show up together. So it makes this degeneracy structure more transparent. Okay, is there any question before I finish this session on geometry? And maybe this is also a good time to stop the recording if it's recorded.